really interested on these topics, and I started to read some book by Stephen Hawking. Do you know him? Yeah, he's really famous. He was a really good theoretical physicist, but he also wrote a lot of popular books on the main topics of modern physics, such as black hole, the evolution of time, Big Bang, and so on. And I was step by step more curious on this, and so that at the end of the high school, I decided to start studying these topics a bit more deeply. So I started to study physics. In Italy, the physics degree is divided by 3 years of bachelor and then 2 years of master degree. In the first 2 years, you cannot choose a lot of exams. So I attend courses on math, physics, of course, laboratory courses, statistics, calculus, coding, and so on. During the last year of the bachelor, I can choose the only exam, and I choose to attend the course on particle physics laboratory. So I started to study cosmic ray. Do you know what a cosmic ray is? Have you ever heard this word? What is it? Yeah. 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 You're very, very smart, very good. So we are always fired by this particle coming from the universe. And they are mostly composed on the Earth by muons. This strange word indicates a particle very similar to the electron, which is more famous, I hope so. But it's just heavier and is not stable. So after about 2 microseconds, the muon decay into electrons and neutrinos. So during this course, I started to study the fluence on Earth of this particle. And this particle arrive on us, and some of them can cross us and cross the entire Earth and go out from the other side. These particles are called neutrinos. And then also for the bachelor thesis, I studied this cosmic ray, measuring the muon lifetime. So in this way, I started my part into particle physics. And I continued on this specialization also during the master. And as I said, it's 2 years long. And during the summer, between the first and the second year, I applied for an internship at the Fermi National Laboratory of Chicago. It is one of the most important for particle physics. And I won this opportunity. I went there for 10 weeks, working with real researchers on the muons experiment. And this was a very interesting experience for my researching life, for my curriculum, but it was also really funny. It was my first time in the United States in a very, very nice city. So I continued to work on the muons experiment, also for the master thesis, the PhD, and I'm still working with this collaboration. As the name of the experiment says, the muons experiment will study the muon to electron direct conversion process. It's a very, very, very rare decay. It's forbidden also in the standard model that I know you already know from yesterday's talk. But I don't want to focus on this. If you're interested on such kind of physics, you have a lot of years at university to study it. And I will focus on the layout of the experiment. This is in construction at Fermilab, so in Chicago, and here at the National Laboratory of Frascati, we work on these donuts inside, at the end, which is a detector called electromagnetic calorimeter. All the particle physics experiments use detector to study particles. In the case of muons, we use a tracker to measure particles' momenta, so their speed, and then a calorimeter to measure the energy of particles, such as electrons or photons. But to understand what I do here, let's go a bit back on the particle worlds. So where can we find particles? How the matter is made? Everything, so also us, are made by particles. If I zoom on my hand or on this desk, I found that it's made of cells. If I continue zooming inside, I found molecules and atoms. Then what there is inside an atom? Protons, electrons, and neutrons. So I subtitle electron because this is a so-called elementary particle. So there is nothing inside the electron. As far as we know right now, there is nothing inside on it. Instead, if I continue zooming inside a proton or a neutron, I found that they are made by 3 quarks each one. And also the quarks are considered elementary particles. So in the history of particle physics, we found there are 5 particles like the electrons: electron, muon, tau, and neutrinos, and they are called leptons. And we also found 6 different types of quarks. Quarks and leptons together are called fermions, and they are the building block of matter. So everything around us is composed by these fermions. And we also found additional elementary particles called bosons. These particles are needed to mediate, to carry the fundamental forces between particles. In particular, weak electromagnetic strong force. The gravity is still not included. We still not found a boson that carry this force. And this is one of the reasons for which the standard model is not a theory and is called a model, because it's not complete. It doesn't include everything, and it doesn't include gravity. So, to summarize, for the moment we found 12 fermions, which are the matter building blocks. We found 5 bosons, which are the carriers of the fundamental forces. And in 2012, we found also, I think, the most famous boson, which is the X one. This is needed to give mass to the other particle. And all of these are the main ingredients of the standard model, which is the model that describes all of our knowledge about the particle physics world. So, but how can we know all of these particles if we can't see the particle? We cannot watch them, because what does watch means? Have you ever think about it? Watch means that a light wave reflects on the object, like this desk. The light bounces off and arrives inside the eyes where the image, the picture, is created. But the dimension of the atom is 1,000 smaller than the light wavelength. So we cannot see particles. The visible light cannot interact with them. So how can we know that there are so many particles? We can study their traces, the interaction with matter. For example, if you see the footprint on sand, on the snow, you are sure that somebody passed from there, even if you didn't see that person. In the same way, we use dedicated material to study the interaction of the particle, and these dedicated materials are called detectors. So, I reported here some pictures of some famous and very big detectors. We can consider the detector as our eye on the particle world. They are needed to take a picture of the interaction with matter, and in this way we can study their properties. So this is the ATLAS experiment installed at a Large Hadron Collider at CERN. And this is needed to detect the particle produced during the collision. And you can see here there is a person, and this is an eye. We can consider an eye tall as a 6th-floor building, so it's very big. Here is a picture of a detector needed to study neutrinos, so the smallest particles. This is in Japan, and this is a huge swimming pool, and here you can see 2 people on a boat. So these eyes are very big. So let's go back on my work here. I work on the electromagnetic calorimeter of the Mutui experiment, so the 2 pink donuts that I showed you before. It will be composed by 2 annular disks. Here you can see the structure of one disk, so they hate like me, more or less. And this disk will be fulfilled by these scintillating crystals. So these crystals we can consider this material, such as descent from the footprint. We are going to study the interaction of the particle inside this material, so with the atoms of the crystals. They are called scintillating crystals because when a charged particle passes through the material, the particle interacts with the atom of the materials and releases a bit of energy. The electron acquires this energy and jumps to a larger orbital. This is not a stable configuration for the electron, so then it will go back, it will jump down to its orbital, and in this jumping, it releases the energy through a photon. So this means that the crystal starts scintillating, starting producing light. Then we need to collect this light with dedicated photosensors. In the case of the multi experiment, we are going to use silicon photosensors, silicon photomultiplier, and the basic functionality is very similar to the smartphone photo camera. So they are needed just to take a picture of the light emitted in the crystal by the interaction of the particle. Then we can acquire the data, so the picture on our computer, and analyze the data. The scintillating light produced in the crystal is proportional to the energy of the coming particle. So in this way, we can measure these properties. Combining the information of several materials, so on several detectors, we can know exactly which particle passed through them. For example, in the MUTU experiment, we use a tracker and electromagnetic calorimeter because we have just electron, muons, and photons. In other experiments, there are also a hadronic calorimeter for a heavier particle or a muon chamber. So in each of these detectors, the particles can interact in a different way. Combining all the information, we can know exactly the particles that arrive inside. It's very important also to know that detectors are developed not only for particle physics researchers, but they are used also in, for example, in hospitals for diagnostic procedures. This is the photon emission tomography that uses scintillating crystal to detect photons. So now I told you what I'm doing here, which is my work and what I did for the PhD. But I would like to give you an overview also on the researcher job. I thought that this could be a very useful information for me at the high school at your age. So I will try to explain you. Of course, what is a physicist? Is a scientist that studies the behavior, matter, and the behavior and evolution inside the space and time. There are two main disciplines, so experimental one and theoretical one. Theoretical physics uses mathematical models to describe nature and also to predict natural phenomena. Experimental physics are more related on experiments, so preparing setup and analyze data and try to validate the mathematical model. And if you want to study physics, there are a lot of researching fields you can go researching on. In addition to particle physics. So condensed matter, astrophysics, mathematical physics, cybernetic information technology, biophysics, and so on. And for all of them, you can choose a more experimental path or a more theoretical one. And for all of them, I think the best and the worst friend is the computer. All the physicists learn to coding from the first year of the bachelor's degree. This is needed to analyze data of the experiment, also to develop math models, simulation, and so on. Of course, in a typical day of a researcher, there are a lot of laboratory tests. Some of us are more focus on the electronics, and so on. These are the main aspects of a daily routine of a researcher, but there are also a lot of additional things, such as presentation, discussion, email, and these are needed to communicate with our working group to arrive and join the same results together. And of course, a researcher will always continue to study, participate to popular events, which means to try to explain its work and the main research topics to people outside the research fields. And also, the researcher travels a lot. For example, tomorrow I'm going to Chicago to join the Mutui collaboration, but we travel a lot also for conferences to discuss our results with researchers of additional or different experiments. Moreover, the physics degree provides also a lot of opportunity, not only in the research world, but also outside. A lot of physicists at the end of the university can go working in business, finance, bank, and so on. A lot of them start working as a consultant for computing and so on. Of course, also a lot of us work in education and some of us in engineering companies. So, to conclude, is becoming a physicist difficult? No, I can tell you that if you're interested in these topics, it's very challenging study this. So it's not so easy, and it's not so difficult if you like it. I want to conclude with this question because a lot of people, when I say I'm a physicist, they say, oh, wow, you are so smart. No, it's just that I like it. And a lot of students don't start this path in physics because they are scared that it's very difficult. But I don't think so. I don't know. It's very funny. And the physics degree can introduce you in an hard but satisfying and fun job. So is very nice, and there is still a lot of fascinating mysteries that are needed to be solved. It's funny also, this stuff, and if you want to join us in the future, we will be very happy. Thank you.